So thank you, everyone. Especially thank you, Professor Alex, for hosting me and giving me opportunity to present my talk. And I'm a senior research fellow at Cryptology and Security Research Unit, Indian Statistical Institute, Kolkata. So today's talk is properties and application of entanglement of indistinguishable particles. And okay, let's start by a puzzle. Suppose in an office, identity cards are issued to employees to distinguish them and track them for some specific task. However, without identity card, they cannot be identified individually. You can see there are two pictures, one with identity cards and one does not have identity card. So one having identity cards, we tell them distinguishable employees with that identity card, and another two don't have identity card, we tell them indistinguishable employees. Now, suppose some task can be completed by employees having identity card. Now the following question arises in the concept of indistinguishable employees. Can that task still be completed by indistinguishable employees? Means employees don't have identity cards. Can the efficiency of the task improve when they work with identity card or without identity card? Does there exist any specific task which can only be completed by the employees having identity card or not having identity card? Well, this question seems a bit complicated in the real life scenarios because we don't know the answers. But in a quantum domain, when we replace employees with quantum particle, we have some interesting scenarios, right? So this is a brief overview of my talk. We'll introduce distinguishable and indistinguishable particle, quantum teleportation, hyperorbit entangled state, and entanglement swapping. And we'll share some of the related research with respect to distinguishable and indistinguishable domain. Then we'll move to our main theorem and the significance of all result. And then we'll conclude and the future direction. Now, all the particle in the world can be differentiated into identical particle and non-identical particle. Non-identical particle are always distinguishable, but identical particle can be distinguishable and can be indistinguishable. Now, what do we mean by identical particle? Means all their intrinsic properties such as mass, electric charge, spin, color are exactly the same. Now you can see in the figure, there are two identical particles, and this is their wave function. You can see the particle with level A has special wave function, which is mainly in S1, and particle B with the special wave function in S2. And you can see that S1 and S2 are non-overlapping. So these two identical particles are distinguishable by the level A and B. Now, when we move this particle close enough, then these two wave functions are overlapped in S3, you can see. Now we cannot tell that which particle is A and which particle is B. So the identical particles are now indistinguishable. In figure A, identical but distinguishable. In figure B, identical but indistinguishable. Now there are some related work. So there are some protocols and applications where people are trying, and protocol which is previously done indistinguishable particle, whether can be done in indistinguishable particle, like quantum teleportation, EPR steering, entanglement swapping, etc. Now there are some properties which were solely for indistinguishable particles, such as duality of entanglement, that was shown by Bose and et al. In 2013. And they were shown that they can also be done using distinguishable particle in 2016. Right. So there are some open questions that is there exist any specific quantum correlation or application that are unique to only distinguishable particle and only indistinguishable particle? Well, quantum teleportation, we all know what it is. It is a process of transferring unknown quantum state from one region to another. You can see an unknown particle with psi x and two particles A or B are entangled, and after this teleportation process with Bell state measurement and classical communication, this psi x is now teleported to psi b. Okay. Now, teleportation fidelity is a measure of the overlap between initial quantum state and the state after the teleportation, and we can measure by this following formula given in equation 1. Okay. Now, without entanglement, like with classical particles, if there is no entanglement between A and B, okay, then the teleportation fidelity bound is 2/3. Now, it was shown by Bennett et al. In 1993 that quantum teleportation can be done with unit fidelity using distinguishable particle. Now, using indistinguishable particle, Low-Franco et al. In 2018 shown that a teleportation fidelity of 5/6. And Margellino et al. Have shown that it is possible to asymptotically achieve unit fidelity quantum teleportation using indistinguishable particle. But remember, it is not exact, it is asymptotically 1. Now the open question is it possible to perform unit fidelity quantum teleportation using indistinguishable particle? Okay. Now, we do have the hyperentangled state. Suppose Alice and Bob has two particles A and B, and 1 and 2 are their specific degrees of freedom. When entanglement exists between similar kind of degrees of freedom, like in figure A, A1 and B1 degrees of freedom are entangled, A2 and B2 are also entangled. So that means they are hyperentangled state. Similarly, if entanglement exists between different degrees of freedom, like A1 and B2 and A2 and B1, that is hybrid entangled state. And when they both exist simultaneously in figure 3, we call that hyper and hybrid entangled state. Now, hyper and hybrid entangled state was first proposed by Lee et al. Using two distinguishable boson. Now there are some open questions. Is hyperhybrid entangled state possible for two indistinguishable fermion? Is the scheme of Lee et al. For hyperhybrid entangled state using distinguishable particle, can it be done using for two indistinguishable particle? If not, can distinguishable particle exhibit hyperhybrid entangled state through some other scheme? Okay, we'll find out later. Entanglement swapping. So entanglement swapping is a transfer of entanglement from one pair of particle to another. Suppose A and B are entangled and C and D are entangled. If we perform a joint Bell state measurement in B and C and with some classical communication to A and D, and after that some unitary transformation, then A and D are entangled. Okay. So using distinguishable particle, the standard entanglement swapping requires 4 particles as a resource along with Bell state measurement. Using 3 distinguishable particles with Bell state measurement is also proposed. Now we go to indistinguishable domain. Entanglement swapping with 4 particles with BSM for boson and without BSM for fermion is proposed by Castellini et al. In 2019. Also, entanglement swapping with 3 indistinguishable particles are also proposed. Now the question is, so we have come from 4 to 3. Now, is it possible to reduce the resource further? Means 2. If it is possible, so we'll require distinguishable particle or indistinguishable particle. Okay, so here we are summarizing all the 8 open questions which we have find out yet. That I'm just repeating for the sake. that are there any quantum correlation and application unique to distinguishable or indistinguishable particle? Is it possible to perform unit fidelity quantum teleportation? Is it possible for hyper-hybrid entangled states for indistinguishable fermion? Is it possible for hyper-hybrid entangled state through distinguishable particle through the scheme of Lee et al. Or some other scheme? Is it possible to reduce the number of particles in entanglement swapping? And then, if possible, it will require distinguishable or indistinguishable particle. So we have answered all these open questions in our paper, recent paper, with my guide Professor Gautam Paul and my collaborator Anindo Banerjee, which is published in Physical Review A 2020. Also, we have the archive link, and the name of the paper is Hyper-Hybrid Entanglement, Indistinguishability, and Two-Particle Entanglement Swap. Now, in that paper, we have proved a theorem that if quantum particle, either distinguishable or indistinguishable, can simultaneously produce and perform hyper-hybrid entangled state and unit fidelity quantum teleportation, then using that, cloning of any arbitrary quantum state is possible. Okay, so I'm again repeating this thing by simplifying that. Suppose we have a quantum particle, and using that, if we can simultaneously produce a hyper-hybrid entangled state, and using that particle, we can perform the unit fidelity quantum teleportation, then the famous no cloning theorem means that any unknown quantum state cannot be copied. We will break that no cloning theorem. Okay, so this is like the famous Bell's theorem analogically. So from this theorem, we can have the two no-go result. Like, so no cloning theorem is the foundation of quantum information. If by some two properties with this no cloning theorem is breakable, like is invalid, then one of two properties must be invalid. So we have two properties, one is hyper-hybrid entangled state, one is unit fidelity quantum teleportation. We know that hyper-hybrid entangled state is possible for indistinguishable particle. So what it concludes, that using distinguishable particle, hyper-hybrid entangled state must be impossible. Why? If using distinguishable particle, hyper-hybrid entangled state is possible, then using distinguishable particle, unit fidelity quantum teleportation is also possible, then we will invalidate the no cloning theorem, right? And that another no-go result is, as we have known that unit fidelity quantum teleportation is possible for distinguishable particle. Then, if unit fidelity quantum teleportation is possible for indistinguishable particle, then using that and hyper-hybrid entangled state, we will also break the no cloning theorem. So here comes the two results our, that no hyper and hybrid entangled state for distinguishable particle, and no unit fidelity quantum teleportation for indistinguishable particles, right? So this answers our one of the first and second and the third question, that we have now a significance of our result. We have a sole property, that is hyper-hybrid entangled state. This is a sole property of the indistinguishable particle. And we have unit fidelity quantum teleportation. This is a sole property of the distinguishable particle. So the bigger picture looks like this. So in this set, we have unit fidelity quantum teleportation is in the distinguishable set. We will explore all the other properties. We have hyper-hybrid entangled state for indistinguishable domain, and the middle, where there are some properties which can be done using distinguishable particle and using indistinguishable particle, right? Now, the rest of the questions. Is HH hyperhybrid entangled state possible for indistinguishable fermion? Yes, we have proved that it is also possible for indistinguishable fermion. And we have shown that no, hyperhybrid entangled state is not possible using distinguishable particle by the scheme of Lee et al. Or by some other scheme. So detailed proofs, I'm not going into the details proof of this. And now we'll answer the rest of the two questions. So here we have answered the question number 4 that HH is possible for indistinguishable particle. And question number 5 is no. Question number 6 is also no. Now we'll move to the question number 7 and 8. So we have proposed a 2-particle entanglement swapping protocol using 2 indistinguishable particles, using the particle exchange method and without using Bell state measurement. So the key idea is we have transferred the entanglement exist between the 2 particle of one, between the 2 DOF of one particle into the 2 other DOFs of the 2 indistinguishable particle. That is inter-DOF entangle to inter-particle entanglement. So this is the number of particle with respect to 2 is the minimum number of particle because it cannot be done using 1 particle. So this answers the question number 7 and 8. Now I will go to the detailed circuit of how a 2-particle entanglement swapping can be done. So this is a circuit. So I'm explaining this circuit. So the blue one is hybrid beam splitter. I will explain what a hybrid beam splitter is. Let's say it's a advanced version of a beam splitter. The green one is another beam splitter. So Alice is in their side, Bob is in other side. So this protocol is basically a particle exchange protocol. This was proposed in 1982 to create entanglement between 2 indistinguishable particles using the particle exchange protocol. So we have used that protocol. So here 2 identical particles B and this B, they are entering in HBS1 and BS1. Okay, now they can either go into this side to Bob or they can be into Alice's side. Similarly, this particle either can go in Alice's side, this particle can go into the again Bob's side. And we have a detector in Alice's side with a PBS, these are the beam splitter, that Alice detects in polarization degrees of freedom and Bob detects in path degrees of freedom, right? So after this circuit, so what this HBS does, HBS creates entanglement between the Alice's particle with polarization degrees of freedom and path degrees of freedom. So what we are doing here, we are just transferring the entanglement between Alice's particle to polarization degrees of freedom to path degrees of freedom to 2 particles which are indistinguishable. We know that which particle is which between their polarization degrees of freedom and path degrees of freedom, right? So this is a circuit for entanglement, and we know that this can be created using a simple arrangement of just PBS, beam splitter, and other optical circuit components. Okay. Now we'll explain what a hybrid beam splitter is. Hybrid beam splitter is nothing but a combination of polarization beam splitter and quarter wave plate. So hybrid beam splitter, so this is a polarization beam splitter, this is R and U, this is 2 mirror, and we place this quarter wave plate here, and this is another PBS, and this is R and U. So this we termed as a hybrid beam splitter in this blue region. Okay. So now we'll show that the initial state which was entering here, this is BHR, BHL 0, and after HBS1, this state is converted to HR and IBD. This is a entangled state between polarization and path degrees of freedom, and this is the final state of this circuit. Okay, if we can analyze this circuit by some CHSH inequality, we show that the shifted value of gate 1 gate Bell violation of the CHSH test into the side-elation bond. So we have now successfully transferred the polarization between path and spin degree of path and polarization degrees of freedom to two particles. So this is a two-particle entanglement swapping protocol, right? So this answers the rest of our questions. Question number 7 and 8. So we have answered all these questions. So now I am concluding my talk. So in conclusion, we have proved that no hyperized entangled state for distinguishable particle, no unit fidelity quantum teleportation for indistinguishable particle, hyperized entangled state of fermions, and a two-particle entanglement swapping protocol using indistinguishable particles. So in future, what we can do from that? We can now find other quantum properties which are solely for distinguishable particle, which are solely for indistinguishable particle. And the other properties like quantum steering and the other properties which can be done using distinguishable particle and indistinguishable particle. We can have a comparative study that for which property we will use distinguishable particle, for which property we will use indistinguishable particle. Like for quantum teleportation, we will never use indistinguishable particle as unit fidelity quantum teleportation cannot be done. But if we have a scheme where we cannot achieve a unit fidelity quantum teleportation, it can be a barrier, then we'll use the indistinguishable particle one. Okay. So now currently we are also exploring this research that we know that we have a relation between the teleportation fidelity and a singlet fraction. So we are also giving a generalized version. So it was given by Horodoki et al. In 1997 for distinguishable particle. We are planning to do it for indistinguishable particles and the particles with multis of degrees of freedom. So, and we show that it has an application in device-independent quantum cryptography. So this is my current research. So this concludes my overall talk. Thank you for listening.